So on December 9th, 2021, I published a sonic gravity episode called Quantum Gravity at the Speed of Thought. And in it I described the Rosetta Stone of the universe, the geometry of the universe, that once I understood, all of the mysteries in theoretical physics just fell into place, and that is a fact. Now I didn't make up the idea that our universe was inside a black hole, and the surface of that black hole is actually a two-dimensional hologram. That wasn't me, that was Gerard Hoof, probably based off Jacob Bekenstein's black hole entropy solution. Stephen Hawking was in on it, and especially Leonard Susskind. There's probably some other guys that I don't know, but you can thank them, because Leonard Susskind figured out that all the machinery and physics and matter and energy in a universe could be encoded on a 2D holographic surface, and that is a fact. And Stephen Hawking talked about Hawking radiation, those black body radiation, heat, and it's the sonic gravity theory of everything, that our consciousness, vibes, soul, spirit, energy, running over the 2D holographic surface of a black hole, encoding a universe inside. And our consciousness receives information from the surface of the hologram the same way our brains receive information from our senses, because our brain doesn't actually experience the physical world around us. All our brain experiences are input signals, bioelectricity, input signals from our nerves and senses, because our brain is really sitting inside a sensory deprivation chamber inside our skulls. It's just interpreting energy that it receives. And the sonic gravity theory of everything is that our consciousness could actually be sitting on the surface of this hologram. And I don't want to blow your mind too bad, but we are the cosmic librarians, the observers in the universe, and we are the mechanism for the law of conservation of quantum information. And we're recording information in our memories and in our DNA. And that's as far as I'm going to go with that one for right now. I don't want to totally freak you out. But later on, we're going to pick up where we left off with that. And then I'm really going to bake your noodle. And that is a fact. Because right now you're orbiting in my sonic gravity and you are viewing the universe through the eyes of a madman. And this is a theory of everything, so we got to be careful not to totally zip off in random stream of consciousness directions. But the main takeaway for this observation that we're making today, right now, in your mind, is our consciousness can only receive information from the changing hologram. So if it's not in contact with the hologram, it's not observable, and it's nothing that we can interact with. It's nothing that our consciousness can interact with, and that is a fact. So if it's off the hologram, it's what we call weakly interacting. It's what we call weakly interacting particles, or WIMPs, or maybe weakly interacting energy is better. We could just call it wee. Anyway, if it's off the hologram, it's wimpy, and that too is a fact. Because one of our limitations as observers is if it's not in contact with the hologram, we can't see it, and that too is a fact. Except that we'll see that the Higgs string, the gravity, is still tugging on the hologram even when matter is orbiting off the hologram. It's still tugging on the hologram, so it's still deflecting space-time. It's still deflecting the two-dimensional holographic surface of the black hole, so it still bends light, and it still has gravity, even though it's off the hologram, and that too is a fact. And in the math, when it's off the hologram, it's what you call a complex number. It will show up as an imaginary number, which is identified as multiplied by the square root of -1, and that too is a fact. But that's what it means in the math when you see a little italicized lowercase I in whatever equation you're looking at. It's off the hologram if it's multiplied by a I, by a little lowercase italicized I, and that is a fact. So I want you to think of the universe as a movie reel, one of those old school movie reels. And every frame in the reel is a picture of the exact energy state of the universe at that instant of Planck time. And if we chop all the frames out of the reel and stack them from the beginning of time, from the Big Bang to the end of time, the distance across the edges of those frames of Planck time becomes time-like, from the beginning of the movie to the end of the movie, across the stack, across the slices of cheese. But for dark matter, the takeaway is that every one of those slices of cheese, every one of those instants of Planck time is one Planck length thick. And you've probably realized that the sonic gravity theory of everything suggests the Higgs field is the gravity field, and the Higgs boson is the graviton. And that the job of the Higgs field, that the Higgs field exists inside the plane of that slice of cheese, of that instant of Planck time, in the frame of that movie. And the job of the Higgs field is to leash the matter and the energy in that slice of cheese, in the universe, to that instance of Planck time. And quantum gravity is the tension in the Higgs string, tension of the string getting dragged across time via time dilation. But now that we understand that each one of those instances of time, each one of those slices of cheese or frames in the movie, that all the matter and energy is leashed to that instance of time by the Higgs field. And you're going to see, and the geometry of that leash is what's going to give us dark matter. And if you didn't see that, check out Dark Matter and the God Equation tutorial, and you'll see what I mean. insane. But quantum gravity uses the Rosetta Stone of the universe the same way. And because the function of the Higgs field is to leash the matter and energy in the universe to its specific instance of Planck time, when we experience time dilation by moving through a gravity field or accelerating through space, that gravity, that gradient in velocity and gravity, we'll see that that actually causes gravity. That causes quantum gravity, and that's the thing that we feel when we accelerate in a car or take off in a rocket. And it's precisely why we don't feel gravity when we jump out of a plane, even though we're moving faster through space, falling, than we do in our vehicle. We feel G's in our vehicle when we hit the gas, but we don't feel G's when we jump out of a plane, even though we're falling down faster than we're going in our car. And I keep saying tension in the Higgs string. Tension in the Higgs string is quantum gravity. And it is. And what that means is when our time is dilated, when our time slows down or speeds up, it's the Higgs field that's trying to keep us leashed to our instance of time. As our time is dilated, that stretches the Higgs string, because the Higgs string's connected to us and it's trying to hold us in one spot. And so when our velocity changes our relative time, or a gravity field changes our relative time, we're going to feel that tug. We're going to feel that stretch in the Higgs string. And when we do the quantum Lagrangian, we'll find out that the reason that tug is happening is because the W boson is forcing a teeny weeny piece of our matter into a dark matter state. And that's what the quantum Lagrangian is, and I will get to that in a different video. And nobody knows what that is right now, because that's the sonic gravity theory of everything. So that is not generally accepted physics, but in order to judge the sonic gravity theory of everything, theory of quantum gravity and the quantum Lagrangian, you have to hear it first. There's no one in physics that will go, oh yeah, I've heard that before. And the only way to assess the validity of a theory of everything is to look at what it predicts, look at the logic and the mechanics behind it, and then check and see if that makes sense with the other things that we know in physics. And guess what? It does. And that is a fact. And I'll try to do a good job of explaining what's woo or new and what's generally accepted, scientific consensus in physics. Because a lot of this is absolutely what is known in physics. So the 2D holographic surface of the black hole is the state of energy across the entire universe at one instant of Planck time. And if we peel the surface of the black hole off and hang it like a sheet, and if we look at it sideways down the skinny 1 Planck length wide dimension of that sheet, the Higgs field, you can think of the Higgs field as embedded in that sheet. And you can think of the Higgs string as anchored inside that instance of time, inside that slice of cheese. And it's leashing all the matter and energy in the universe to that one instance of Planck time by the Higgs string. And so it's really like a tether. And the sonic gravity theory of everything accepts Einstein's two main axioms of relativity. One, the invariance of the speed of light. The speed of light is the same for all observers. And two, the equivalence of gravitational and inertial mass, which is the weight induced by acceleration is fundamentally the same as that induced by gravity. And it's called the equivalence principle. And that's actually a big clue, because the weight induced by acceleration is quantum gravity. But it's not described like it is in Newtonian mechanics, where force equals mass times acceleration. Even though that's true, in quantum gravity, it's all about time dilation and the stretch in the Higgs field as we accelerate, as our time dilates. But it's actually kind of the same thing, which makes a lot of sense, because it's not just space, it's space-time. And the Newtonian law of gravitation is all about mass in space. But mass is just energy, and space is space-time. So quantum energy is time gravity, the same way that Newtonian mass gravity is space gravity, because it's space-time and mass is energy, so it's all the same. And that is a fact. Now, that's not necessarily the scientific consensus, but it is the sonic gravity theory of everything, and I think it's pretty obvious when you think about it. Or maybe it's a little arrogant to say it's obvious. I think it's obvious if you are looking at the universe through the prism of the Rosetta Stone, the sonic gravity Rosetta Stone of the universe. But I think it's undeniable that what I'm saying about mass is energy and space is space-time, like that is consensus. And it's pretty elegant. And you'll see there's kind of a beautiful symmetry with what we already know about gravity. And if you don't see it yet, you will see in just a minute. Okay, so first I want to explain a little bit about what time dilation is. And so we're going to look at kinetic time dilation. And this is completely accepted special relativity in physics. This is not controversial at all. So what I'm drawing up for you are two what we call photon clocks. And since we accept the invariance of the speed of light, we know that the speed of light travels constantly at about 300,000 kilometers per second, and nothing can change the speed of that photon, which is light. And there's a little photon inside a cylinder, and there's a clock on the top of the cylinder. And that photon goes down, it bounces off the bottom of the cylinder, and it goes back to the top. It goes down along path A and comes back to the top along path B, and when it hits the top of the clock, that's when the little hand moves a tick. And since the speed of light never changes, the clock maintains perfect time, and that is a fact. So now in clock one's going to sit still. Photon's going to go up and down and run the clock that way. Now in clock 2, it's the exact same clock as clock 1. It's got a photon in the middle too, and the photon in clock 2 is going just as fast and identical speed as the photon in clock 1. But now we're going to slide clock 2 sideways. And what happens is the photon that's in clock 2, it's still going up and down inside that cylinder, but as you slide that cylinder over, the photon doesn't really go straight up and down anymore because it has to stay with the clock, so it kind of has to go at a diagonal. And you can see that because the speed of that photon is exactly the same in clock number 1 as clock number 2, because clock number 2 has to go at a diagonal, the same distance A that both photons cover in the same period of time, since clock 2 had to go at a diagonal, A doesn't get it all the way to the bottom of the cylinder. And so it has to use a little bit of B to get to the bottom of the cylinder for it to, and then when it bounces back up, B isn't really long enough. B isn't a long enough distance that it covers over the same time as clock number 1. When clock number 1 hits the roof of the cylinder, B has not hit the roof of the cylinder yet. And that is a fact. And that's why the faster you move through space, the slower you move through time. Because the time in clock 2 is going to tick slower than the time in clock 1. And that too is a fact. That is kinetic time dilation. And the opposite is true. The slower you move through space, the faster you move through time. And that is a fact. And when our time dilates, when we speed up and our time dilates, that's called passing through the curvature of time. Your time is changing from constant and it's curving to a slower time or a faster time or what have you. And it's actually passing through the curvature of time the same way passing through the curvature of space that's caused by some kind of mass energy denting the space-time. Passing through curved space causes you to experience gravity, but passing through that curvature of time also causes you to experience quantum gravity, and that is a fact. Because it's not space, it's space-time. And everybody knows that the energy of mass curves space and causes gravity, and that is a fact. So, there's no reason to think that kinetic energy velocity won't curve time the same way that mass energy curves space. Because velocity and mass is just energy, and space and time is just space-time, and that is a fact. And then there's gravitational time dilation. We talked about Einstein's bedrock principles of relativity, that inertial and gravitational force is equivalent. So in the same way that kinetic energy, velocity, causes time dilation, there's gravitational time dilation. And the deeper in a gravity well we are, the slower we move through time. And the further out of the gravity well we are, the faster we move through time. And that too is a fact. And so now, up until this point, the sonic gravity theory of everything and everything that I've talked about, none of this is controversial to this point. This is all well-established, scientific consensus has accepted it. And if you were to post this on Facebook, you wouldn't get banned for spreading misinformation. Probably, maybe, I'm pretty sure. I don't know, maybe you would. Hard to say. And that too is a fact. So we're about ready to get into time dilation and how time dilation causes quantum gravity by pulling energy, like mass energy, across time, through the curvature of time, through different slices of cheese, so to speak. But first we need to talk about how energy in systems is modeled. And so I want you to think of a cliff, and on that cliff is a rock. Now when the rock is at the top of the cliff, it's a certain height, and there's two kinds of energies in a system. There's potential energy, and then there's kinetic energy. And really potential energy is height/gravity energy, and kinetic energy is velocity energy. And so when the rock is sitting on top of the cliff at the maximum height, all of the energy in the system is potential energy, and that's given as the mass times gravity acceleration times the height. Now that thing rolls off and falls down. As it goes down, it trades its potential energy, which is its height, for kinetic energy, which is speed. So as it falls, it gets closer and closer to the ground, and as it gets closer and closer to the ground, it gets faster and faster. And so at the very end of the trip, from the top to the bottom of the cliff, right before it hits the ground, it has zero potential energy, and it's all kinetic energy. So in that moment, the mass times the gravitational acceleration times the height equals 1/2 mass times the velocity squared. And this energy relationship, because the energy is fixed, there's only a certain amount of energy in the system. And at the beginning, it's all potential, and then at the end, it's all kinetic in this particular example. Now, the Lagrangian, instead of using forces on the rock and describing it with all these Newtonian mechanics, the Lagrangian uses the energies in the system that we just talked about, and it summarizes sort of dynamics in the system. But any function that generates the correct equations of motion in agreement with the laws of physics can be taken as a Lagrangian. And the Lagrangian is given as the kinetic energy minus the potential energy. And if you sum that over time, over the time that you're measuring the system, the sum of the Lagrangian is what we call the action. And I'm not going to get into the action right now, but what I want you to remember is that when you look at the Lagrangian, which describes the dynamics in the system, the Lagrangian is the kinetic energy minus the potential energy. So it's like the velocity minus the gravity, so to speak. That is a fact. Now, up to this point, there is nothing controversial in pretty much anything I've said so far. But here's where the sonic gravity of everything sees quantum gravity, where the scientific community hasn't seen it so far. And I've said this all the time, a whole bunch. Every time I start talking about the sonic gravity theory of everything, quantum gravity is tension in the Higgs string. And that tension arises because the Higgs field leashes all the matter and energy in the universe to our instance of Planck time, to our slice of cheese. And we've talked about how velocity and gravity creates a curvature of time, which is the same as pulling matter and energy, dilating their time, pulling that matter and energy into a different slice of cheese backwards or forwards in time. And it's that tension in the Higgs field that's dragging that matter or energy through the curvature of time to a different slice of cheese, so to speak. And so let's take a look at the example of a rocket. Now, a rocket takes off. You're inside this rocket. It takes off. It's accelerating. It's getting faster as it launches and flies through the air. Now, that acceleration slows down your time, because when you move faster through space, you move slower through time. But it's also leaving the Earth's gravity field. And as you pull out of a gravity field, your time speeds up. So gravity is speeding up and velocity is slowing you down. And since we know the Lagrangian is the potential energy, which is where you start, remember our example of the pebble on the cliff, the potential is where you kind of start. So the rocket is moving your potential energy, speeding up your potential energy because you're coming out of that gravity well, which pushes your time forward a couple slices of cheese. But then you're accelerating, and your acceleration is pulling you back into a slice of cheese in the past. And so the tension between the potential energy pulling you forward and the kinetic energy dragging you back at the same time kind of pulls you tight from both ends. And if you do the Lagrangian, if you do the kinetic energy minus the potential energy, you get a negative kinetic energy minus a positive potential energy, and it comes out to really negative time dilation. Because it would be like -1 minus a +1, which is -2, which would be a lot of tension, a lot of negative energy density, a lot of tension in that Higgs string. And for another example, you could take a car. You jump in your sports car, you hit the gas. Now you're accelerating, which is slowing your time. Except for you're staying at the same level of the Earth, right? Because the road, you're kind of at the same level of gravity in the gravity field, because you're on the surface of the Earth. And so your time is slowing down from the acceleration, but then the gravity is trying to keep your time right where it is. So the Lagrangian is the kinetic minus the potential. The kinetic is slowing your time down, so that's like a -1. And then you subtract the potential energy, but you're not going anywhere. It's not changing, so it's like a -0. So the Lagrangian would be a -1, which is some tension. It's half the tension, say, in the rocket, where you've got the potential energy cranking you forward and the kinetic energy dragging you back at the same time. This is just your kinetic energy trying to drag you back. But you still feel that tension in the Higgs field. You still feel that negative energy density, that pressure as you accelerate. Now, on the other hand, take skydiving. Skydiving, you jump out of a plane, and it's kind of nice. Just don't open your mouth. And when you take the kinetic energy, now you're accelerating because you just jumped out of a plane. So you're accelerating through space really fast, which slows your time down. But remember, you start off where the potential energy is, just like you start rolling when you knock that pebble off the hill. It sort of starts at all potential energy. And you see, because you're falling deeper and deeper into the gravity well, the place where the potential energy starts is falling back through the slices of cheese at the same pace that the kinetic energy is pulling your time. So everything matches, and you never pass through the curvature of time, because the potential energy, which is the place where you sort of start from, is dragging back, and it's following with the time dilation from the kinetic energy. And what that looks like in the Lagrangian is kinetic energy minus potential energy. So you have kinetic energy, which is -1 because you're going faster, and then you have a minus, but then the potential energy is also -1 because you're falling deeper into a gravity well. So you have -1 minus a -1, which is the same as a +1. So you have 0. And that's why there's 0 tension in the Higgs field when you skydive. There's 0 time dilation when you jump out of a plane, even though you're moving way faster through space, falling, than you do in your car. But you feel gravity in your car because of the Lagrangian. You feel no gravity when you skydive. And that's why Einstein famously said, if you want to escape the force of gravity, jump off of a building. And that sounds crazy, but that's what he meant, and that is a fact. And this is not particularly controversial. The only thing that I think nobody's really thinking about, or nobody has envisioned in terms of quantum gravity, is the Rosetta Stone of the universe, which is the movie reel, the slices of cheese, the frames in the film. That's the only thing, I think, that image is the only thing that the scientific community hasn't put together yet. And it's exactly how we derive the equation for quantum gravity, and that is a fact. But this is how time dilation causes gravity, moving through the curvature of time. And quantum gravity is that tension in the Higgs string as it stretches across time dilation, as it tries to do its job to leash the matter and energy to our instance of Planck time. And when the time is dilated, it will stretch the Higgs string. And the stretch in the Higgs string is what you feel as G's, as acceleration. And that is probably a fact. Maybe, probably. I'm pretty sure. No, I'm totally sure. That too is a fact. So now it's time for the main event. Now we're going to derive the equation for quantum gravity. And since we know that quantum gravity arises from tension in the Higgs string across time dilation, we're going to model the tension in the Higgs string the same way in statics and dynamics that we model the tension in a spring. Now, a spring has a stiffness that we call K, and that stiffness is the force that's required to stretch the spring a unit of distance. And so K times the distance, D, is the force in the spring, and that is the force of quantum gravity. It's the tension in the spring, which would be K, the stiffness, times the time dilation, D. So quantum gravity is the tension in the Higgs string, and the more time dilation, the more quantum gravity force. Now, in Newtonian gravity, the force of gravity between two masses, the force equals the gravitational constant times the first mass times the second mass divided by the distance between those masses squared. Now, for quantum gravity, which is time, just intuitively from Newtonian gravity, knowing that space-time is both space, the same way it would be Newtonian gravity and quantum gravity or time gravity, I'm going to start off in the derivation of the equation dividing the distance of the stretch times the stiffness of the spring. I'm going to divide it by t squared the same way Newtonian gravity is divided by r squared, because in Newtonian gravity, the further apart you are, the less the gravity is. And in quantum gravity, it makes perfect sense to me, and there's kind of an elegant beauty to it. It should be divided by t squared, and that makes perfect sense because if you say you have some time dilation, but it takes you longer, more t, more time to achieve that time dilation, then you're going to feel a lot less gravity, right? And that's like the difference between going 0 to 60 in 3 seconds or 0 to 60 in 60 seconds. The shorter that t is, the time that you occur, the time that it takes to accomplish that time dilation, the shorter that is, the more gravity you're going to feel. But if you're going 0 to 60 in 60 seconds, that's divided by 60 squared. And so that's going to really cut down on the amount of g-force that you're going to feel. So now let's derive the equation for quantum gravity. We got energy, which is a joule, and the units of a joule is a kilogram times a meter squared divided by second squared. And then force, a newton, is a kilogram times a meter divided by a second square. And so the force, which we know has to be in units of kilogram times a meter divided by second squared, we're going to take the energy of mass, which is what we're going to accelerate or time dilate, times the stretch in the Higgs string, which is a unit of length, which will go with meter. And then the stiffness of the Higgs is a force, which is a kilogram meter per second squared. And then we're going to divide it by t squared, because like we said before. Now, so the energy of mass is E equals mc squared. It's actually 4 pi divided by the g factor times the observable mass times the speed of light squared. But just for simplicity's sake, we're just going to say mc squared, which is kilograms times c squared, times m for meters for the unit of length, the stretch in the Higgs string, and then times the stiffness of the Higgs, which is a kilogram meter divided by second squared. And then we're going to divide it by s squared, which is the dividing it by t squared that we talked about. So then when we kind of do all the math and cancel the units, we're still looking for our force. It's got to be in kilogram meters divided by second squared. But now we have kilograms squared, c squared, m squared divided by s to the fourth. Okay? So we want kilograms, we got kilogram squared. We want meters, we got meter squared, and we want time squared in the bottom, but we got time to the fourth in the bottom. And then we have this pesky c squared in there that we need to get rid of. And so now what we know the equation has to be to get all the units to come out right is we have to square root the whole thing. Because if we square root kilogram squared, we get kilograms, which is what we want. If we square root meters squared, we get m, which is what we want. And if we square root s to the fourth, seconds to the fourth, if we square root that, we get s seconds to the second squared in the denominator, which is what we want. And then of course we got to get rid of that pesky c squared, so we gotta divide our equation by c squared from the beginning so that we get rid of that c squared. So that way, if our equation is the energy of mass times the distance in time dilation times the Higgs string stiffness divided by t squared divided by c squared and then square root, that derivation will give us the exact force units that we need. And that solution will give us a force of quantum gravity. And that is a fact. Now, the only thing that's impractical sort of is knowing what the time dilation distance is across these slices of cheese, because how do you do that? How do you sort out what that distance is? Because it's a distance, it's not really a time. Might be a time, but it's just hard to say. So what we do is we take a look at all of, and this is exactly what they did for Newtonian gravity too. Anyhow, and it makes perfect sense. And so what you need to do is you need to look at, you have constants in that equation, which is c, which is the speed of light, and the Higgs stiffness. We don't know exactly what it is, but we're going to assume assume that it's constant and elastic so that it doesn't like change over time. And we don't think it should because there's no changing or elasticity over time in regular Newtonian gravitational mass gravity. So I think it's a pretty reasonable assumption. And the time dilation is determinable based on the height and the velocity. That can be calculated. And the energy of mass, whatever we're accelerating, is measured value. And t squared is proper time. So that's just the time over which the acceleration happened. So we could actually boil all of those constants into a gravitational constant the same way they do in Newtonian gravity. And so then it would be the quantum gravitational constant times the time dilation in seconds, which we can compute, times the energy of mass, which we can compute, divided by t squared. So it actually looks almost exactly like Newtonian gravity, which there's kind of a symmetry there. There's sort of a beautiful elegance there. Now, does that mean it's right? I don't know, but it's hopeful. Not because, and it's not elegant and symmetric because we looked for something elegant and symmetric. We modeled quantum gravity as tension in a spring across time dilation, which is totally rational. I mean, it just makes all the sense in the world. And it reduced to this. Right? We had no intent to make it pretty. We just kind of used our brains. We modeled it the way we thought made sense. And it just reduces to this gorgeous equation that looks almost exactly like mass gravity, which it should, because mass is energy the same way velocity and time dilation is energy. And it's not divided by r squared, it's divided by t squared. And all the units come out, so have a nice day. So, but the way we would determine what that gravitational constant is we would just accelerate something. And we would record the force, we'd calculate the time dilation, and then we would solve for g. Because the force can be measured from an accelerometer. And then we'd record the time, we could compute the time dilation, and we know how big the mass was, so we could do the energy. We could figure out the energy of the mass, and then that force that we measured would have to be all of those measurements that we did times g. And so essentially, we could compute a g just based on that acceleration experiment, and then do a second acceleration experiment of non-identical measurements. And the g that we computed for the first one would have to solve the second one, the second experiment, for it to be right. And that would be a fact if it was right, which I'm pretty sure it is. So the force of quantum gravity squared equals the energy of mass times the quantum time dilation distance times the Higgs stiffness divided by the time squared over which the time dilation occurred divided by the speed of light squared. And we can boil all the constants down and bake in all the conversion factors with an experimentally determinable quantum gravitational constant with two experiments. And then the equation for the force of quantum gravity becomes the quantum gravitational constant times the kinetic seconds of time dilation minus the gravitational seconds of time dilation, just like the Lagrangian, times the energy of mass divided by t squared divided by c squared divided by t squared times c squared. And so the force of quantum gravity is the square root of the quantum gravitational constant times the Lagrangian of the time dilation times the energy of mass divided by t squared times c squared. And that is probably a fact. Maybe. Probably. I'm pretty sure.